Welcome to the RE4AFAGRi online training videos. The RE project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement 96/35/30. In this extended video, we will go through the MLAT model in terms of its general features, its running and tailoring. First of all, in terms of model introduction, please make sure to check out the MLAT software installation procedure video, which is a separate training video that reports detail on all the necessary steps to configure your environment for operating the MLAT model. In this video, instead, we will focus more on its concept, its functioning, its results, and its customization. So in terms of technical requirements, please make sure to check the other video, while for gaining a general understanding of how the model works and how to concretely run it, please keep watching this video. First of all, to provide a background on electricity demand, just a general background, it's important to bear in mind that around 10% of the global population still lives without access to electricity, and the vast majority of these populations are concentrated in the sub-Saharan African region. Therefore, energy demand data is crucial for understanding the current gap and planning solutions, including power system planning tools. However, the challenge is that often the requirement is to assess a demand that is not currently existing, also because there is no electricity access infrastructure in many areas, in particular in rural areas, but would, however, be there if electricity access was available. And how could this demand evolve over time? So how can we project its potential evolution over time under different socioeconomic transformations? In this context, the MLAT model is the electricity demand module of the RE4AFAGRi modeling platform, about which you can learn more about in the specific videos of the RE4AFAGRi modeling platform and the specific videos of the other models part of the platform. MLAT is an electricity demand assessment platform that covers all the main demand sectors relevant to electricity system planning, and it models them in high spatial resolutions with the objective of making future projections along different scenarios, and also having a specific target on communities where currently electricity supply infrastructure and access are lacking or limited. So the RE4AFAGRi platform, as you can see from the diagram here, is composed by 4 main modules, and the role of the MLAT model is pivotal because it produces inputs in terms of electricity demand for NEST, the integrated assessment modeling of energy, water, and land, and for the onset bottom-up energy access supply-side planning tool, while it receives input from the water crop model in terms of water needs and constraints for irrigation that affect strongly the agricultural-related demand for energy in rural areas. So MLAT, what is the objective of MLAT in the RE4AFAGRi modeling platform? Basically, it is to produce spatiotemporally granular estimates of the latent electricity demand in different sectors for an entire country. So it is designed to run at a country level, but to have a high level of granularity across sectors, space, and time. It was originally introduced in a scientific paper by Falquet et al. In 2021 and is written in the R scientific computing programming language. It exploits a variety of geospatial data sources and subnational statistics to produce monthly estimates, so seasonal aware estimates of electricity demand in a set of sectors across a given country. MLAT was developed by a large team of researchers. Some contributors are listed here, and it is in active development, and a growing community of users is active. Here are some examples of the spatial and temporal granularity of the outputs of onset. So, some jargon that is useful in better understanding the context and the functioning of MLAT in the RE4AFAGRi modeling platform. The important distinction between actual energy demand, which is the demand that is currently consumed or projected to be consumed in the future, and the latent energy demand, that is the energy that would be consumed if the infrastructure and the socioeconomic conditions to achieve given goals were in place. So a demand that, for instance, is not fulfilled because there is no sufficient power supply in a region, or because people have big constraints on their ability to pay for electricity, they would be happy and glad to consume a given amount of energy to do certain things at home or in their businesses. However, due to their limitations in income, for instance, they are unable to be so. So this is latent energy demand, as well as farmers in rural areas that would like to process their crops, but they don't have electricity available, so they are forced to do this manually. So MLED estimates, depending on the configuration and the specific scenario that is run, can include both the actual and the latent electricity demand, or in other runs, you can also model, for instance, the actual demand and disregard the latent one. So it's flexible to consider either one or both. As a reminder, so electricity demand is a function of several things, different sectors, from residential to productive sectors and public and community services, and also of different drivers, such as macro drivers of population, economic development and growth, the availability of infrastructure, and the spatial and temporal components of geography, land, urban-rural distinctions, the climate role in determining energy demand, as well as the seasonality across periods of the year or hours of the day. It is tightly connected also with the dynamics of the economy, so population and economic growth, the land use decisions, so decisions on agricultural sector or on expansion of cities, and with other sectors. The water sector is crucial here, since we're focusing a lot on rural areas, so the water needs have requirements for pumping the water and supplying to the fields, which imply energy use. Climate change, as the water demand, for instance, is affected by the climate, but also the temperature can have an impact on the energy demand. And with some policy pushes that occur at the national or subnational level, such as industrial and development policies that push the evolution of energy demand. So MLED, considering all these different characteristics and drivers and determinants of energy demand, works in a fashion where demand projections are both driver-driven, that is to say, determined by, for instance, the projected growth in population and economic affluence level. However, also they can be objective or policy-driven, so basically ensuring that certain decent living standards are achieved, such as sufficient electric energy to cover powering pumps for irrigation, for processing, or appliances in school and healthcare facilities is provided. So the model is both considering what is kind of endogenously happening as a consequence of changes in society, and also by exogenally targeting certain objectives. It relies on geospatial data processing algorithms. It is very granular and bottom-up in fashion, as in certain sectors it really models appliances and their utilization given certain needs, considering stochastic variation in the electricity demand. And it also has a scenario logic. So basically, it follows the definition of scenarios in terms of economic, demographic, and climate pathways to assess how they affect the future evolution of energy demand and latent energy demand. The underlying assumptions of MLED have been discussed through the years with a broad array of stakeholders in different countries of Sub-Saharan Africa, with practitioners, policymakers, to adjust basically what are the main assumptions and mechanisms coded in the model. Also, some field visits have been carried out to assess the current patterns of plants ownership and use and evaluate how to best reproduce them in the model. And also, the model is aware of the existing literature and of needs-driven objectives that concur to define the assumptions to estimate the demand. 6 main sectors are represented in the MLED. From the residential sector, both households with current electricity access and households with latent demand, so without access that will gain access in the future. So separately, these are represented. And then in terms of commercial and entrepreneurial activity, non-farm SMEs, mining in terms of heavy industry, crop processing and irrigation for agricultural productive uses, and school and healthcare as social infrastructure sectors. These are represented separately as different modules of the model to estimate demand in different sectors in human settlements at cities, towns, and provinces. In terms of spatial resolution, as you can see from the chart, MLED is designed to operate at the country level, so to calibrate the current electricity consumption level, the initial levels of consumption with recent national statistics, and downscaling them, spatially distributing them at the local population cluster level. And being a bottom-up assessment platform, MLED performs calculation at the most granular level allowed for by the input data. So in the case of residential, SME, health education, for instance, really calculations are done at the population cluster level, which are small units over space, such as towns, villages, communities, small cities, up to metropolitan areas, continuous settlements of people in a country. And then, depending on the sector, we also carry out calculations such as around the communities at the Voronoi cluster level, or at the subnational level for the growth in drivers of population and economic growth, and up to the country level when aggregating outputs and calibrating the demand with national statistics. The advantage of this granular resolution is that outputs are produced at different level of resolutions, from the very local native scale of the analysis of the population clusters, so output are really granular, can show the estimated demand at a very local level, up to an aggregation at the subnational and national level that can be very useful for policymaking to get a picture of the overall evolution in a country and its regions. Moving to the temporal resolution, basically depending on the sector, there are also here different resolutions at which calculations are carried out. For some sectors, like the appliance-based ones, education, health, residential, water pumping, the original calculations are even at the hourly level to assess the utilization patterns, while in other sectors we focus on the monthly level, as it is sufficient to get a sense of the seasonality. And in certain sectors which are very stable during the year in terms of demand, such as mining, we simply carry out the calculation at the yearly level. Overall, after the outputs of the model are aggregated at a time-year time steps, so we have evolution by 10 to 10 years, but the monthly seasonality is explicit in time steps, so in the default output files. For instance, we have for future year 2030, the expected demand for each sector in each specific month of the year separately, and then in total for the whole year. In terms of model structure, MLED has a modular structure, and it can be disaggregated into four main types of models. A modular structure means that there are separate scripts that are responsible for the different steps of analysis. The backend modules are the modules where libraries, working directories, and technical parameters are defined. So the modules that are run, let's say, at the beginning of the model, that are not particularly required to be edited by the user, except for some setup parameters such as the working directory, but then are loading the required dependencies to run the model. The scenario model instead is where really the user is required to take a look and provide modifications, because it is specific to the country in question, and also it contains the specifics of the scenarios that the user wants to run. So basically the assumptions, the input data, the parameters, and so forth, which are defined by the users in terms of what type of run they want to obtain and for which country. And each country has a specific file. Then the modeling modules are those where actually the calculations and the data operations are happening to calculate the estimate. So the user is not directly actually required to open them, to check them, but in case of willingness to change some hard-coded modeling assumptions or to gain a better understanding of the functioning of each module, then it's a good idea to also take a look at them, but they are automatically called by the model itself when running an analysis, so they do not need to be run manually. And finally, we have output writing and reporting modules, which at the end of our run basically write the output files and the summaries and some reporting data in terms of checking what are the results of the model run. So in the RE4AFAGRi modeling platform, as we have already seen, the MLED model basically receives inputs from the water crop model in terms of water demand for irrigation that affects water pumping energy and crop processing requirements. And then it provides output to the onset and the nest models. So the electricity demand that is estimated in MLED goes into the onset model to assess optimal energy access solutions and systems, and to the nest model to basically plan the energy system in synergy with the water and the land sectors. So water crop provides crop-specific, month-specific, time-specific irrigation needs for each scenario. Also the yield, so the yield of the crops, the current projected yield in response to given irrigation input, and it provides in raster format as gridded data these data files, which are then read and processed in MLED for each settlement's clustered agricultural catchment area, as we will see shortly. And these are used to assess pumping energy and crop processing energy demand. And then the outputs of MLED that are linked into the onset and nest are written in different spatial resolutions to match the resolutions of these models. So the onset outputs are written at the settlement level resolution, which is the same of the native resolution of MLED, to be processed in in onset. So you can see really the granular resolution in the image of the settlement output data. Instead, for nest, outputs are summarized and written at the river basin catchment area resolution, which is the native resolution of the message nest model. So areas such as those visualized in this figure for Zambia. When we access the MLED code folder, which as you can see in the video on the installation and configuration of the MLED model, we have a set of files, of R files. These R files are the files that provide the different modules that I was talking about before. And the most crucial file is the MLED hourly file, which is the so-called homepage of MLED, where we basically defined the very basic technical and run-specific parameters, the scenarios that we want to run, and then where we basically launch the code to perform the analysis and run the model. As already detailed in the installation and configuration video, line 8 is the working directory. So we need to update it to the working local folder on our computer in terms of working directory. It needs to be manually inputted. And line 10 instead is the database folder. So basically where we should specify the path to the cloned Zenodo repository containing the input data to run the analysis. Again, for additional details on this, check the configuration and installation video. Note that there is also a download data parameter, so it's possible to actually let the MLED model download itself the data from the Zenodo. This is an alternative option, but if you have done it previously, actually the recommendation is to leave it to false. Otherwise, this will toggle a download at the beginning of the run that will take some time to retrieve the input data from the Zenodo. So the MLED model and file, when launches, it first initializes the scenarios, then runs analysis, and finally writes the outputs at different spatial scales. It produces as output summary CSV files and results, which can be found inside the results folder inside the MLED working directory. So the key message here is that the beginner, the really beginner user that is just trying to replicate an analysis for an existing countries of the MLED, countries that are already developed, basically is only required to open and intervene in the MLED hourly R file. All the other modules are basically called from here, so there is no requirement to open and run those files manually. So the next slides from here basically provide an overview of the functionality and underlying mechanisms of each module to get an understanding of how the module works. But the user, the beginner user at least, is not required to intervene onto them. First of all, the backend module, which is run at the beginning of each session of R and of each session of MLED, is the model responsible for installing and loading the required libraries to run MLED, as well as to download or collect the input data from a specified country run if the download data option is on, so it will automatically get the files from Zenodo. Basically, as you can see, you can take a glimpse. The backend module is checking that all the required package dependencies that are necessary to run MLED are installed on the on the environment of the user, and if they're not, it will automatically install them, download them from the internet. So you require an internet connection to run MLED and to download them. The potential useful tweaks for the advanced user could be to tweak the CAL parameter in line 15, which defines the number of percentage of CPU cores to run for parallel processing. So this means that R and basically MLED can exploit the fact that computers can carry out many operations in parallel if they are sufficiently powerful, and we can exploit more computational power to perform heavy geospatial operations in parallel. So if we are operating on a very powerful machine, we can increase the number or share of clusters that basically are used to perform operations. However, if you are overcharging this option, supercharging, then basically this might lead to memory errors, as we are requiring too many resources that are not available in our computer. So only tweak this option if you are an experienced user and you know what you're doing and you know that your machine is sufficiently strong to support this increased load. And note that this option is only relevant if the allow parallel parameter that is found in line 16 of the main MLED file is set to true. Otherwise, if this option is set to false, the computer will not exploit parallel processing. Then moving to the scenario files, which are really the core areas where instead the user might really want to take a look and to check the assumptions, parameters, and the input data, are these files which are found in the country scenarios subfolder of the MLED folder, and they are the place where all the main input data subsequently called by the different MLED models are defined, as well as where country-specific parameters for model calibration and affecting demand estimations are defined, such as the national electricity demand in different sectors, so the official statistics that are used for calibrating and downscaling the initial level of demand, and technological parameters and country-specific input data are red. Note that in current implementation of MLED, 5 countries have been developed: Zambia, Rwanda, Zimbabwe, Nigeria, and Kenya. So scenario files for these 5 countries are available. And so basically it's possible to try runs for these 5 countries, while if you want to develop runs for additional countries, check the second part of this video where we focus on how to develop new country analysis. Note that the scenario models is itself wrapping different other modules, so basically different things are happening when the scenario models is run. One is the projector module that basically is responsible for projecting the key macro drivers such as population, GDP, and GDP per capita and urbanization level along the SSPs, which are some shared socioeconomic pathways, which are assumed evolutions for different scenarios in these major drivers across countries, and inferred growth rate. So basically how a given country is expected to change in terms of GDP, population, urbanization, economic development in the future for different scenarios. And the nice thing is that this is happening at a heterogeneous growth rate within countries. So based on this scenario, not all regions and provinces in a country are growing at the same rate, but they are changing in different ways, and this is represented by this model and this script. The urbanization calibration script is also part of the scenario model, and it calibrates clusters into urban or rural, calibrating from the national urbanization rate and its future evolution over the SSP urbanization projections up to the target year of the model, which is in default 2060. And this methodology is based on the original onset approach developed by Mentis et al. So here you can see an example of the calibration algorithm. If before calibration there is a bias based on the gridded urbanization data, which does not converge or match with the statistically reported urbanization rate by the World Bank, the calibration model of the urbanization makes sure that the post-calibration status of urban-rural of clusters is consistent. Another preparation module called by the scenario model is the demand growth weight. So we convert a relative wealth index to an absolute wealth estimate to basically gain an understanding of how different regions and settlements in a country are standing in terms of their wealth level, in terms of their GDP per capita, level, so that we know how rich or poor different areas inside a country are, with a very high level of spatial granularity, which is important for assessing current and future demand, and then at what pace policy objective imposed by each scenario for a given target year, such as universal energy access, irrigated cropland, or crop yield are reached. So depending on basically the evolution of GDP per capita, we project the speed of evolution in different development targets. Finally, we have the electricity access module, which, based on the methodology developed in Falquet et al. 2019, based on nighttime lights and built-up area, it basically estimates at a very local level the prevalence of electricity access or lack of electricity access to gain a sense of where the most of latent demand is currently found within a country. Another preparation model is the Create Clusters Voronoi polygon, which basically is a model responsible for creating Voronoi polygons around the center of each population cluster polygon. You can see a representation here. For instance, you have centered a population cluster where you can see from the satellite imagery certain buildings. So that's the unit of analysis of MLED. And then you can see that a large polygons around it is built, which captures the agricultural land around the population cluster, so the fields, basically, which are not built up, they don't contain buildings, but they are somehow cultivated by the people that live in these buildings, presumably. So basically, these additional polygons are serving the purpose of capturing the agricultural land around each population district. There are different toggles that can be tweaked to basically adjust how these polygons are constructed. The most important one is the M radius buffer cropland distance parameters, which basically adjusts how large should these cropland polygons be, and this affects how different amounts of cropland are linked to different population clusters. If we reduce this distance, then we consider that very remote cropland that is far from population clusters is considered standalone, so it's eligible only for off-grid demand and not for on-grid demand, or let's say supply source that is linked to the local community. So it's estimated as a separate sector suitable only for off-grid electrification, such as standalone solar pumps or diesel pumps. Then, moving to the actual demand estimation model. For the residential sector, we have the residential.R module, where, as you can see from this chart, we basically, depending on the locally estimated electricity access rate, we estimate the demand and its growth over time for different group of people. So starting from people who have already electricity access today in the calibration year, so where only demand is coming from people with electricity access, here's 2020. And then moving into the future, considering both the growth in the blue bars, so in the demand from those that already today have electricity access, and the fact that some people, of course, depending on the scenario assumption, will gain electricity access in the future. And so this additional demand will sum up to the existing demand and its growth, and will continue then to grow in the future. So it's kind of a multiple group or cohorts of electricity access, those that already have it today, those that will get it tomorrow, and those that will get it the day after tomorrow, and how these different components each grow and sum up together. So basically, this dynamic process is considered and modeled in the residential module, and it's dependent on the currently estimated and calibrated electricity demand and electricity access rate, and how the different policy targets and endogenous socioeconomic drivers are driving the evolution over time of electricity demand and electricity access. Note that the residential module estimates demand evolution for those that already have access proportionally to the locally projected GDP per capita growth rate, mediated by an income elasticity of electricity demand coefficient. So basically, this is a standard approach in energy economics that the change in electricity demand is responding to a certain elasticity factor. So for each percentage change in income level, in GDP per capita level, the electricity demand will respond and grow to another given extent. And this is based on the very local subnational GDP per capita projections that are estimated as shown before in the cluster. Instead, for those who will gain access to electricity at a given future time step, first, households are allocated to a given tier or level of electricity access, which is estimated through a statistical model based on the currently existing distribution of tiers among population who has access. So suppose that today we know that clusters with a given wealth level have a certain level of energy access, then we can assume that that settlements that will have a similar wealth level in the future, and when they gain electricity access, they will be expected to have a similar level of electricity access to those today that have that affluence level. So this kind of similarity or resemblance approach is used to attribute a given future demand to communities that today have no access to electricity. This is based on the tier specific, urban rural specific appliance basket generated with the RAMP model outputs. You can check the Lombardi et al. Paper, which describes how RAMP works, but basically an appliance characterization has been carried out to define typical, archetypical baskets of appliances and their use and consequent electricity demand for different tiers of wealth, of consumption, of urban, rural settlement. The health and education modules work somehow in a similar fashion, so they refer to existing data on the spatial location of healthcare and educational facilities, which are input data to the model. And then basically they are projected to converge to a universal electrification of all facilities, inclusive of a densification and enlargement of existing facilities. So basically the fact that the number of educational and healthcare facilities should grow, should expand in the future, and all of them should gain access to electricity. And the extent, the size of the energy demand linked to each facility is proportional to the number of beds or the number of pupils for school. And these are then mapped to a given tier of demand for schools and healthcare facilities, which, similar to the residential demand, have been estimated starting from appliances in the RAMP model. When it comes to the agricultural sector, we have three main modules, basically. One module that is responsible for reading and processing the water crop output data, which provides the water volume needs in a given area for meeting some irrigation needs. Then we have a water pumping energy, which is basically a module simulating the operations of a pump to extract water from surface water or groundwater sources and to distribute them onto the field. And then we have a cold storage and processing module that basically estimates the requirements of energy to process and store the local production from crops, according to certain policy targets of how much local processing we would like to achieve in the future in a given area. So the crop module basically reads the water crop output data, processes them, and extracts them at the level of the population settlement cluster. So it links a given water need to a population settlement clusters using the Voronoi polygons that were explained before. The pumping module simulates the operation, the technical parameters of a pump, basically referring to the local aquifer depth or to the local distance and slope with regards to surface water bodies. And it also selects whether at each cluster it is best to develop surface and groundwater irrigation. The crop and processing, the pumping modules basically have two twin options, as I was mentioning before. So if cropland is too remote, so if it's further away than the value of the M radius buffer cropland distance, then this demand is represented separately as a demand that is only suitable to be covered by decentralized energy access solutions, because it's very far from the community, so it's not suitable, for instance, to be supplied by a local mini grid, and it's only suitable to be supplied with decentralized pumps. Finally, the crop processing catchment areas is a module that basically assesses how far is a given agricultural production site from the nearest or most accessible city market hub, so a location where the crop production can be brought and sold. There is a parameter, which is the minutes cluster parameter, that can be tweaked, and basically it defines the extent. So you can see in this picture the pink area, which is the area within a certain travel time from a certain market city hub. So you can play with this option to extend or shrink basically the coverage over space of areas that can be accessed within a given travel time and that are deemed suitable for basically crop processing. So we estimate that only areas that are sufficiently in reach of a market are suitable for local crop processing. The crop processing model itself estimates then, based on a database which was built up from literature research, that provides energy intensity for crop processing and cold storing certain types of crops. So it's crop specific, and if the production falls within the crop processing catchment areas, then we estimate how much energy could be locally required to locally process those products, which then could be sold at the locally accessible markets. Of course, this depends on the local yield, crop yield and production, and of course also their expected growth over time as derived from their water crop model. The other productive sector module basically instead focuses on non-farm SMEs, so other type of productive demand which is not related to agriculture, and it's tightly linked on the residential electricity demand through a markup range. So basically we have this range SMEs markup parameter which defines which percentage of the residential demand could also be contributed to by the other productive sector, so it's additional to the residential demand. And this basically the value between this defined range is proportional to the residential sector demand with this range factor. And in each cluster, it can range between these two values that we define in the range parameter based on the local employment rate, road density, and basically these two elements are kind of a proxy of the labor and economic situation of a given community, how active and vibrant is the local entrepreneurial community. And then the SME's future demand evolves at the same growth rate of the residential demand at each cluster. Moving on to more heavy industry sector, we have a representation of the mining demand. So basically we take the national reported demand from the industry sector and we specially downscale it using the mining database from C2.2 2020, proportional to the measured nighttime light radiance from the Colorado School of Mines from those sites. So we distribute the total industrial demand, which is defined in the scenario model with the parameter industry final demand tot, onto the clusters based on where we know that mining activity is taking place and proportional to the intensity of light radiance that is observed in those areas. Then the mining demand is projected to grow in the future at the local growth rate of GDP per capita. Some additional modules that also are optional, so are not necessary in the strict sense to run the model, are the calculated growth potential that basically, based on the water growth outputs, it calculates how much the future yields could change in response to irrigation, so how the production of agricultural products could improve locally thanks to given change in irrigation intensity. We then have some conclusive modules, so a cleaner module, which basically is responsible for rearranging the results, column names, order and structure, as well as for calculating the other sector, which is kind of a residual sector, a statistical residual sector, if we find a discrepancy between the total reported demand from IIA and some estimated demand in the base year. This could be, for instance, for some sectors that are not represented in MLED, such as electrical transport. This cleaner module produces summary CSV files and figures, so to get a glimpse, basically, at the end of a model run of what are the total estimated demand and its evolution in the different sector in different years, as you can see from this image example, and also some CSV files which contain disaggregated information. And in addition, then, of course, the output data, as we will shortly see, are written and produced at the end of a model run. Moving to the scenarios, assumptions, and country definitions in MLED. So, by default, MLED is prepared to consider the RE4AFAGRi scenarios, which, as can be explored on the RE4AFAGRi.Africa website, are 3 storylines that have been designed through a workshop to basically assess and compare different futures with increasing level of ambition across energy, water, and food objectives. They consider certain targets of, for instance, electricity access, in terms of improving nutrition security, and in terms of irrigating and crop processing a certain amount of agricultural productions. They have underlying assumptions in terms of SSP, so in terms of population and economic growth, as well as RCP, so in terms of climate change mitigation and impacts. How are these scenarios defined in the MLED? So basically, to customize and take a look at the different scenarios, the user can take 2 main types of action. One is simply in the MLED hourly file, where basically it's possible to specify the different SSP and RCP scenarios, the policy target, and the scenario names. So these main targets that were shown in the table in the previous slide can be rather easily customized in these lines from 55 to 75 of the MLED hourly file. And in addition to that, it's possible to directly edit the scenario country files. So for the country scenario that you are interested in, the country model that you would like to develop, basically directly editing the parameters and the assumptions for each country file throughout the scenario file script. And in particularly between lines 101 and 725, which are all lines that define parameters, technical, economic parameters, and then call to the input data to read the input data in terms of the different energy, land, water, socioeconomics, and so forth. So directly accessing this file, the file are commented. So mostly lines of code are commented to inform about which operations each line is carrying out, which data it's importing, so that they guide through the customization. Moreover, the wiki page on the RE4AFAGRi GitHub for the MLED model provides a very detailed representation and description of all the lines of code and input data and parameters, so that you can gain a really detailed understanding of what to change if you want to change. Moving to the model calibration, MLED is designed to operate at the country level, so at a very granular level for an entire country. So before projecting demand in the future, the model is calibrated to the base year, to the current electricity consumption level using recent national statistics, which are downscaled at the local population cluster level. In particularly, the calibration considers a set of different values and statistics, from the national electricity access level to the total electricity demand, and then its disaggregation into the residential, industrial, and other sectors. We mostly refer to data from the International Energy Agency World Energy Balances to do this type of calibration. The rationale behind how demand projections are made then depends on the sector and typology of final users. So for instance, for the residential sector, demand is divided between households with and without electricity access. And then, as described before in the residential module, basically there are different assumptions on how to project into the future, starting from the calibrated value. But from the non-residential sector, demand is projecting following other assumptions in terms of GDP per capita growth or in terms of a certain markup range tied to the residential sector for the SMEs sector. And in other sectors, then demand is projecting following targets like policy pushes. So for health and education, there is a target to converge to a universal electrification of all facilities by a given target year. So to gradually bring electricity to all health and education facilities. Also according to required densification of facility to cope with keeping demographic growth. And for crop processing, basically also there, it's a target-based growth. So basically the scenario encapsulates an assumption on which share of crop production should be locally processed by a given target year, and then the model ensures to converge to this policy objective. For irrigation water pumping, instead, the kind of demand is exogenous as it comes from the water crop model and the scenarios that are modeled in the water crop model to, again, achieve certain targets of food security and food production. As already described, urbanization is also calibrated as part of the scenario file to ensure that the urban level and the share of clusters that are considered urban in the analysis are consistent with the statistics from the World Bank. So how do we run MLED? Now that we have described it, characterized it, and prepared our environment following the video on the installation, we can now think about running the model. So to perform a run in our studio, first of all, the user should open the MLED hourly file, the homepage of the model, into the RStudio. Then, as already described, we should update, make sure that our working directories and data directories are updated with the paths on our local computer where we retrieve the databases. And then, of course, check in detail again the software installation procedure video, ensure that all the packages, dependencies, and libraries are installed and the model configuration has been completed. Then the user is required in line 21 to specify the country or countries, can also be more of them, separated by a comma, on which to run the model for. As specified, the current implementation of the model has been prepared for 5 countries: Zambia, Zimbabwe, Nigeria, Kenya, and Rwanda. However, the user might want to develop an own country analysis. So in this line 21, the name of the country run should be carefully spelled and included, as this will call the different files and scenario files and input data files specific to that country. After this, basically the user is required to select all the lines in this command, in this script. So basically, as shown here, with Control-A or simply from the Edit menu, select all, so that all the lines of this MLED are stripped or selected. And then simply click on the Run button to initialize a run. In this case, how can we see that MLED is running? Well, besides the fact that the console will be busy, so you will see this red button visualized here that tells us that something is happening. Also, a log file will open automatically, and the log file will basically keep us posted on the development of the different stages of model run. So as the model goes through its different modules and steps, we are informed about it, and also we are keeping track of how much time this takes to complete. How much overall does it take to complete? Well, it really depends on factors such as the CPU speed of the local computer, whether we are using or not these parallel processing options that we were talking about that can be customized in the backend R file. Also, the size of the country and the complexity of the underlying input data matters a lot. So a small country will be completed much faster than a very large country due to the lower amount of calculations to perform. And also the number of scenarios, right? So we can, from the MLED hourly file, decide whether we want to run 1 scenario, 2 scenarios, or a larger matrix of scenarios. And depending on this, of course, the total runtime will multiply. As a benchmark, running one scenario for Zambia and writing all output files, so from the very high resolution cluster ones to the national summary files, on a Windows 11 PC with a 12th generation Intel Core i7 CPU and 64 gigs of RAM and a parallel processing of 50% of GPU cores takes about 1.5 hours. However, as mentioned, note that the first runtime ever will be slower because the backend file will install all the required package and dependencies. So, of course, the following runs will be much weaker as they will skip this initial configuration phase. In terms of outputs, we get several files which are hosted inside the results folder of the MLED folder in the RE4AFAGRi repository. And in particular, the main outputs written are the onset output job package, which is a cluster level. So it contains all the original population clusters with a lot of additional fields, each specific reporting calculated statistics by the model. So the local electricity demand in the different sectors, in the different years, in the different months of the year, as well as additional computed variable as part of the model analysis. But then results also summarize at the nest level. So at the river basin level, this is handy if you intend to run nest as a follow-up, while the first output is, of course, useful if you want to run onset as a follow-up. So being MLED a key input to both the onset and the nest models as part of the RE4AFAGRi modeling platform, we automatically produce outputs that are ready to be used in these two supply-side models. Then for policy purposes, the results also summarize that the second level of administrative unit with a geo package aggregating the result at provinces. Also, this is the scale at which results are visualized in the online RE4AFAGRi dashboards on our www.re4afagri.africa website. And finally, we also produce very aggregated country-level summary CSP and figure results that can be useful to have a first glimpse of the total results of a given run. Here in the figures, you can see an idea, for instance, of how the cluster level results can look like at a very fine spatial resolution, but also how a very aggregated CSP country level result is appearing. To check out the high resolution results, we recommend interactive GIS software like QGIS that can be used to directly browse, point and click, and observe the distribution of the estimated energy demand across a country or within specific clusters and provinces and communities. But then a major question that might arise from the discussion that we had so far is how to run MLED from a given country or region of interest. We have seen that so far 5 countries are available, but the question remains on how to expand the pool of countries for the interested user of MLED for an own country. So a number of steps are necessary to do to carry out to basically implement MLED in a new region. The first one is, of course, look for data. There are some country-specific datasets which are not included in the Sub-Saharan African-wide database of MLED, which include, for instance, a population settlement cluster file, graded population data, nighttime light data, the nest basin catchment area files, if we also intend to run nest as a follow-up, and also geocoordinates of healthcare facilities and schools. Also, then we will need to adjust the statistic in the scenario file. So basically, we need to find statistics on population, on energy demand, on urbanization rate, and on additional features and characteristics of the country that are specific and needs to be updated to the country that we intend to run in the scenario files mostly. It's very good practice to also discuss with stakeholders. So basically to tailor the specific assumption, the socioeconomic, technological scenario, and policy assumptions to the country in question. Not all countries are behaving the same, have the same dynamics, and can be represented the same assumptions. All the different parameters, such as those that I'm showing here, might be very different and can find different realities in different settings. So it's important that the values of these parameters are discussed with people who are experienced of the country in question and of the specific sectors that this parameter represent. Another possible option, including which is also part of this assumption, is the appliance baskets and usage patterns. So what type of appliances will newly electrify households and facilities use and what patterns? So this might be updated to rerun the ramp model that generates basically this archetypical load demand outputs that are assigned to newly electrified households and facilities to deal with the latent electricity demand aspect that is represented in onset. So also this might vary much across countries. So it's good practice to revise these baskets and usage patterns to make sure that we are assigning the right loads to the people and the facilities in the future. So let's make an example. What if we want to prepare an omelette for Ethiopia? It's just an example. It's not part of the current pool of countries available. So it's an example of a country that we don't cover yet, but we would like perhaps to cover. So to do that, first of all, we would need to create a new folder inside the database, omelette database folder. So the data folder that we downloaded from Zenodo. If you open it, you will notice that we have a country studies folder inside this, where we have a set of countries folders, which contains the country-specific input data. So we might want to add a folder called Ethiopia for the new country study that we want to develop. So create a new folder manually inside here, the country studies folder, and name it Ethiopia. Of course, you would also need to update the country study parameter in the mlet.r file, as was shared before, in line 21, country study, renamed to Ethiopia. Then we would need to create a scenario Ethiopia file. The scenario files are contained in the country scenarios folder inside the mlet code repository on our computer. So we would just start perhaps by copying as a template one of the scenario files for the countries that we have already available and rename it to scenario Ethiopia if in our case we want to develop a country model for Ethiopia. So for instance, we take the Zambia one, just a random one, or the Kenya one, and we copy paste the file and we rename it to scenario Ethiopia. This will be our starting point, and then we will need to edit to adjust the data and assumptions for the Ethiopian case. So then, in fact, we will need to open this file and work extensively to basically manually update all the major statistics and information for the country of Ethiopia, looking for the different sources that were presented a bit in the previous slide, or from any other sources that you are confident and find reliable for these different parameters that you can get a glimpse here and that are commented mostly in the script. And also, if you open up the wiki page on the GitHub of the RE4AFAGRi repository, you can basically find all of them listed and documented what they mean, what is their unit, how they should be inputted, etc., etc. Looking for data. Of course, we would need to look for population settlement cluster files. There are multiple sources, so this is just an example, but if you look online for population clusters, population settlement clusters, there are multiple independent research bodies that have produced this type of clusters. The grid-free is a handy one because it covers virtually all countries in sub-Saharan Africa, so it's a recommended option to access, but then many organizations have their own approach of generating population clusters, or you might want to generate them yourself. This is beyond the scope of this video, but any type of geometrical features that represent human settlements is a good option. But here we show the example of downloading from the grid-free website. So on the grid-free website, you can freely download as a GeoJSON file, so a geographical explicit polygon file, the population settlement clusters, and as well as the population estimates in terms of gridded population data. So beyond the population clusters, we also need gridded population data. But for the grid-free, for instance, not all countries are covered, and Ethiopia is a case where it's not covered. So in this case, you need to recur to alternative sources. Also here, gridded population data is widely available across the world for many countries, for many providers of data. We provide here the example of the WordPop, because WordPop is another reliable source that provides gridded population for virtually all countries in the world. So here there is a link, and it's an option to consider to find this gridded population data for Ethiopia. As for night and lights data, the standard recommendation here is to refer to the Colorado School of Mine virus, NASA virus satellite imagery for night and lights data. Here's a handy link to download it. It's a very heavy file, so we would need then to crop it for Ethiopia and to make it available to the country input folder. So we need to download it and crop it along the Ethiopian boundaries and move the output result to the country input folder. By the way, all these files that I'm listing, also the previous one, the population one, should all go in the country input folder that we created at the beginning of this tutorial. So the new Ethiopia folder inside the country-specific data folder in the data repository. In terms of additional data that you need to find for the country, it's the geo-coordinate of healthcare facilities, which can be found in many cases online by reliable sources, but maybe the very first best is to always ask local stakeholders, such as local ministries of health or of education, and otherwise you can also look in online repositories. There is a growing availability of open data in this sense. The important thing is that this is geographically explicit coordinates of where healthcare facility is, and basically the same goes for schools. There are many options, even when it's really difficult to find something, like when this exercise was first designed in September 2023. On Google, it didn't seem possible to find easily a georeference database of education facilities in Ethiopia. So in these cases, you might recur to tools like OpenStreetMap. Please check also here the link on the slides to see a tutorial of how to basically scrape healthcare or educational facilities data from tools like OpenStreetMap, or rather also engage in conversation with local stakeholders who surely have this data, such as the Ministry of Education, but simply maybe it's not available easily online. So yeah, on the OpenStreetMap, you can basically extract information that was added on the public map by people, by crowdsourcing of information. So here you can see the city of Addis Ababa, for instance, making a query of school on OpenStreetMap allows us to get all these coordinates, which are tagged positions of school in OpenStreetMap in Addis Ababa, and we can export this data as a geo file, which we can use then for MLET. For the Nest Basin catchment area files, in case you are interested in running Nest as a follow-up of the MLET run, I suggest you to ask Adriano Vinca, who is part of the RE4AFAGRi project, who is a key developer in the message Nest team, to basically gain access from him to a country-specific Nest file. But this is only required in the case that you would like to run Nest as a follow-up of the run of MLET. Otherwise, you can skip this step. Then you would need to prepare the clusters data. So once you have downloaded the population cluster data, such as in the case of Ethiopia, you would need to use this script, which is called process clusters. It's contained in the country scenarios folder in the RE4AFAGRi MLET code repository. It's already prepared. You would just need to customize it a little bit, changing the input data files, basically, to adjust the input data file that you just have downloaded, such as the file name and the location of the clusters data, of the gridded population data, and so forth, the assumption in terms of parameters, and so forth. And this step is necessary to prepare the clusters data to then be in the format that is required by MLET to run into MLET, basically. It will add some fields and make some calculations that are those that then we can use as an input of population clusters into MLET. These process clusters, as I was saying, it's pre-prepared. So it's in this folder. You just need to update it a little bit to the country that you would like to prepare the clusters from, update the file name, and then run it and wait for it to write an output file that will be our clusters to be used into the MLET. This requires adjusting things like the urban population share, the electricity access rate, the total population, And for instance, an option is using the World Bank data as a reference to adjust these values. While we launch this process clusters file, we will then have an output file in the data folder named as the country that we just are trying to process. So the Ethiopia, in this case, you will see a new big job package file will appear, and this is our output data that we really need for the new country to run MLET. We then need to adjust to add additional files. We can use, again, as a template, some other country folder, like the Zambia one, for instance, and update the files that need to be mirrored copied from the other folders. So we have this CSV file which contains some assumed load profiles and calendars of crop demand, for instance. These files are to be copied inside the Ethiopia folder from the Zambia folder or from another country's folder, and if relevant, the assumptions need to be adjusted inside them. We also need to do some slight coding modifications. So when it comes to processing, in particular, the health and school facilities, given there is no standard format of these files, we need to basically classify them into different tiers. So we need to create a field called tiers and classify based on the type of facility into 4 categories based on their size, centrality. You can follow the example here. For instance, you see that we name, if we call facilities which are hospitals of level 4, clinic of level 3, health post of level 2, and rural health centers of level 1. So we create kind of a classification. The important thing is that we create a field called tier that divides into numerical orders from 1 to 4 the facilities in a country, where 4 is the most central and largest, and 1 is the most remote, small, and rural. Then what we need to do, we need to basically update the file names in the scenario Ethiopia file. So we'll open the scenario Ethiopia file that we created, and for a bunch of input data, such as the clusters and the grid population, we need to replace the file names. And this should exactly match those in the Ethiopia data folder where the new data has been copied or downloaded, and all the names must be replaced. Be careful, because missing even one will lead to a file not found error and model breaking. So this is a very detailed process that needs to be done with a lot of care. For instance, in the clusters line, in line of code 202 of the scenario file, we need to write the file name that came out of the process clusters file. So the process clusters that we calculated need to be inputted here as a file name, and the same goes for gridded population in line 217 and so forth. If you really want to also update the appliance basket, you will need to refer to the ramp model. Here is the link and the documentation. So basically on how to produce new tiers and baskets of appliances, and how to make new simulations of what could be basically archetypical loads for the country in question for people and facilities gaining access to electricity. It is always an option of using the one that were already pre-calculated if you do not really see reasons why those in your country should be very much different from the pre-assumed ones. To do this, we are providing the ramp model code and input data into the ramp folder of the MLET database folder. So there you can basically exploit this file and these input assumptions to generate the output profiles. This is beyond the scope of this video training, but all the code and documentation are linked and available. And in case of issues, of course, please feel free to reach out to us or open an issue on GitHub to get specific support on this specific aspect of baskets of appliances and archetypical loads generation. You would need to adjust this type of basket of appliances and utilization patterns files according to your assumptions before running them. Okay, after all these steps have been carried out, once we are ready to run our new country analysis, we prepared the input data, we prepared the clusters, we created the folders for the new country in both the data and in the scenario file for the new country name. We updated the assumptions, the data files, the parameters, everything is ready. So now we can just select all the code in the MLab hourly file and click on run. A good idea, if the code succeeds, is that we check, first of all, the results folder and this summary result to get a first sense if the results look right. So if we did everything right, the results should be looking in quite logical. The order of magnitude of the total national demand should mirror in the baseline year the current statistics and the current values in terms of direct hours and division across sectors, and also the future evolution should look reasonable to our eyes. If instead you are facing errors, troubles, or there are some warnings that are appearing while you are carrying out this procedure for your new countries, please check carefully the steps that were just described. So to conclude, to get any additional contact and help, please refer to the RE4AFAGRi platform official GitHub webpage, where you basically can open issues in the issue section. And in the issue section, you should type a well described clear title and a detailed description of basically what issue are you facing, what is your system configuration, what are the steps that you have followed so far, where are you getting an error, can you please also post the exact error that you are receiving or the problem, maybe you cannot find some specific data or you're struggling on how to process it. Well, feel free to open a query here or also to contact us via email at re4afagri@gmail.com for having more direct support. But however, a good practice is to post directly on GitHub so that also other users can contribute and help the community effort. So thank you very much for following this extensive training on the MLED model. Please make sure to stay in touch with us by following updates on the RE4AFAGRi.Africa websites, where you can find additional free open source modeling tools, data and documentation, also additional tools that are complementary to MLED, for instance, free business decision support tool. Many countries are also under development, so more countries are to come, also thanks to active involvement of participants to trainings activities like this video. And please follow our channels also for additional videos and training materials and training videos that are upcoming in 2024 in terms of availability of information and support. Thank you very much from the RE4AFAGRi project.